So let's start with the B tree today. So B tree is again a tree data structure, and it has certain properties that it stores the data in the sorted form, and all the operations, the basic operations that can be performed on B tree can be done in logarithmic time, just like searching, insertion, and deletion. So we will take an example of B tree. Before that, let's go through some of the properties of B tree. So one of the most important property of B tree is that all the leaf nodes are always going to be at the same level, and it is also known as M-way search tree. The reason is the earlier tree that we have seen were actually the binary trees. Binary means the number of children that we can have is 0, 1 or 2. But here the tree can be expanded to 3 number of children, 4 number of children, and so on. So general form of B tree can also be known as M-way tree, and of course this is going to make the data in sorted form, so it is also known as M-way search tree. So if I take a B tree of order M, we can interpret so many things from this given data. The first thing is the maximum number of possible children will be equal to M. So just like we have seen in case of binary tree, binary means two-way search tree. And in case of binary search tree, the maximum number of children for a particular node can be equal to 2. Whereas in this case, when we talk about M-way search tree or B tree of order M, the first important thing that we can interpret is that the maximum number of children possible will be equal to M. Similarly, what will be the minimum number of children? So if we talk about leaf nodes, because some of the node are going to be the leaf node, so the minimum number of children will be equal to 0 for leaf node. And for all the internal nodes, the maximum number of children possible will be equal to ceil of M by 2. Right? And similarly, when we talk about number of keys, so maximum number of keys will be equal to m minus 1 because the maximum number of children is m. So the keys will be equal to m minus 1. Similarly, for all the root nodes, the number of keys can be equal to ceil of m by 2 minus 1. So you can remember either of the number of children or number of keys because both of them are interchangeable. So you can just identify the maximum number of children. If you can identify the maximum number of children, you can automatically identify what will be the size of key. And the last important property is that all the insertion that we are going to perform will be done at the leaf node. So when we start inserting the data, first of all, the data will be inserted at the leaf node. Then we check the property, whatever we have seen here. And if the property is not going to satisfy, then we try to split that node, and we'll just see some of the steps that how we are going to perform that. So let's start with an example. We consider an example of order 4. We have taken order 4 here. The reason is for odd number of orders that would be pretty easy. So you can try the same question with order 5. So let me take an example in which order is equals to 4. Now as for the properties that we have seen, we can interpret some of the things. The first thing is if the order is 4, that means the maximum number of children possible for one node will be equal to 4, and the maximum number of keys will be equal to 3. Right? Similarly, you can see that what will be the minimum number of children for internal node. So that will be 4 by 2, that will be equal to 2. And ceiling of 2 will give you 2. So in this way, we are going to create a tree of order 4. Let's take an example. Okay, so let's say this is the list of key given, and we need to create a B tree of order 4. So the maximum number of children for a node can have is equal to 4. So initially the node is empty. When the node is empty, we are going to store only one data. And now you can see that this particular value 12 has two pointers on the left and right. So this is simply going to point to the values which is less than or equal to 12 towards the left, and the value which is greater than or equal to 12 towards the right. So when we insert the first node, the number of elements will be equal to 1. Then we start with the second node. Now, when you place this element, you need to understand that data is always stored in the sorted form. So compare this value 8 with 12. 8 is less than 12, and if 8 is less than 12, then 8 will come first followed by 12. So now you will create a node. In this node, you have two key elements, 8 and 12. Again, you can see that there is certain points here which is going to point to the child nodes. Next, when we insert 13, again compare 13 with 8. 13 is greater than 8. Move one position right. Compare 13 with 12. Again, 13 is greater than 12. Therefore, again move this 13 1 point right. So now you can see that after inserting 30, the number of key elements we have is equals to 3. And if you have seen the property, then you can say that the order of this particular B tree is equals to 4. Therefore, the maximum possible key in one node is equals to 3. So till now, all the things are going smoothly. Now let's try to insert one more value, and let's say that the value is 6. So now you compare 6 with 8. So first of all, you will try to place 6 at its own position. Now when you place 6 at the correct position, then the next step will be to split the node. So now you can see that the maximum possible value can be equal to 3. So four values in a single node cannot be accommodated. Therefore, we need to split the middle element. So as I told you that in case of order odd, let's say order is equals to 3, 5, 7, and so on, it would be easy to identify the middle element, right? Let's say if the order is 5, you can easily identify the middle element, and that element will go one level up. Whereas when the order is even, and if I need to identify the middle element, I have two options. Either I can take here as 8 middle element, or I can take 12 as a middle element. So now this is up to you. You can either select 8 or 12. Let's say I'm selecting 12 as middle element. So when you select 12 as middle element, this middle element will go one level up, and rest of these nodes are going to be towards the left and right child. So when 12 will go one level up, all the elements which is less than or equal to 12 will become the left child of 12, and all the elements which are greater than 12 will become the right child. So in this case, 6 and 8 will become the left child, and 13 will become the right child. If you split the element with 8, then 8 will go one level up, 6 will go towards the left of 8, and 12 and 13 will go towards the right of 8. So both of them are the correct option, but I'm selecting 12, and throughout this problem, I will always select this element to be the middle element. So if you are selecting the tree which is having 8 as a middle element, then throughout the process, you have to select the element which is at the second position. So make sure that whenever you're selecting any particular node, you follow the same pattern to complete your problem. After this, we can insert 2. So compare 2, and as I told you that all the elements are always inserted from the leaf node. So this 2, first of all, will be inserted at the leaf node. Compare 2 with 12. 2 is less than 12. Go towards left. Compare 2 with 6. So 2 is even less than 6. Therefore, this will become the left of 6. Similarly, we can insert 19, compare 19 here, go towards the right and insert 19 after this element 13. Now we'll insert 21, so 21 will go directly after this node 19. So you will have 13, 19 and 21 in single node. There are 3 keys. Now when we insert 1, so when you can see the position for 1, 1 will go towards the left of 2. So when 1 will be inserted, again we need to show that the total maximum keys possible in a single node in order 4 will be equal to 3. So now you can see that this node cannot accommodate 4 number of keys. Therefore, we need to split the node. Earlier we have splitted the node from this index. So here again we will split the node with 6, and 6 will go one level up. Now when you are moving 6 at one level up, you again need to see that this node should not exceed the maximum number of keys. So here when you move 6 one position up, you can see that this node is going to contain 2 keys, which is valid in this case. So now 6 will go one level up, and this is how the B tree is going to look like. So when 6 go one level up, you can see that in this particular node, we have 2 key element, and correspondingly, there are some pointers which is going to point towards the child node. So all the elements which are less than equal to 6 will go towards the left child. The element which is in between 6 and 12 will go as the middle child, and all the elements which are greater than 12 will become the right child. Similarly, when we insert 15, so you can see that 15 is going to be inserted at the leaf node. and this is going to be placed in between 13 and 19. So after inserting 15, again you can see that the total number of elements here becomes equal to 4. However, the maximum possible elements are equal to 3. Therefore, we again need to split the data. This node will be splitted in such a way that one of the key element will go one level up. So here again 19 will go one level up, and you can see that now the root node is going to contain 3 elements, 6, 12 and 19. In the left of 6 you have 1 and 2. In between 6 and 12 we have 8. From 12 and 19 we have 13 and 15, and all the elements greater than 19 will go towards right. This will be equal to 21. So you might have observed one thing, that splitting is always done after inserting the key value. So make sure that you do not perform this splitting before inserting the data, because we need to identify the middle element after inserting the key that we are going to process currently. Similarly, we can insert 29. So 29 will be inserted towards the right of 21. No issues at this point. Then we insert 5. When you insert 5, 5 will be inserted towards the right of 2. And just because the value is less than 6, this is going to be towards the left child. Then comes 39. So no problem at this point again. 39 will be inserted towards the right of 29. Now let's see what happened when we try to insert this element 3. So 3 will be inserted in between 2 and 5. When you insert 3, you can see that the total number of keys at this particular node is 4. However, only 3 maximum keys are allowed in a single node. So we again need to split the node. When you split the node, 3 will go one level up. But when 3 goes one level up, you can again see that this particular node cannot accommodate more than let's say 3 number of keys, because the order is 4. So when 3 goes one level up, the number of nodes in this particular, the number of keys in this particular node becomes equal to 4, which is not possible in case of a B tree of order 4. Therefore, when 3 goes one level up, we again need to split this root node. So how we are going to split? So when 3 will go one level up, the elements will be arranged in this way: 3, 6, 12 and 9. So again we will take the middle element, that is 12. 12 will go one level up. On the left of 12, you will have 3 and 6. On the right of 12, we will have 19. Now what will happen to the rest of the elements? Make sure that rest of the elements are located in such a way that this is going to follow the property of a search tree. So what will be in the left of 3? The left of 3 will be equal to 1 and 2. So you can see that the left of 3 is 1 and 2. Similarly, on the right of 3 we had 5. And this 5 is also less than 6. Therefore, 5 will be placed in between 3 and 6. Similarly, when we talk about 8, so 8 was on the right of 6. So here again 8 is on the right of 6. Similarly, in between 12 and 19, we had 13 and 15. So what will be on the left of 19? Left of 19 will be equal to 13 and 15. And rest of the elements which are greater than 19 will be towards right. Therefore, 21, 29 and 39 are towards the right. So now you can see that the property of B tree is maintained. All these nodes are leaf nodes, and these leaf nodes are always at the same level, and this is also going to be one of the search tree, right? So this is M-based search tree. When you start traversal from the left hand side, you can see that all the elements are sorted. You can see that 1, 2, 3, 5, 6, 8, 12, then 13, 15, 19, 21, 29 and 39. So all the elements are sorted, and therefore this is an example of B tree with order 4.